My name is Natalia and I'm a math tutor. This is my first video ever, all thanks to Grant Sanderson and his beautiful idea of making this summer a Summer of Math Exposition. I am going to talk about matrix diagonalization and in particular when it's not possible. I chose this topic because not long ago I was teaching one of my students linear algebra and I realized that the non-diagonalizable matrices are not given enough attention throughout the internet. This video is made for the students of linear algebra who are already familiar with the idea of linear transformations and the change of basis of such. Some contact with eigenvalues and eigenvectors will also help, but it's not necessary. Let's begin. First, let's go through a usual case of matrix diagonalization. The aim is to factorize the given matrix T into the multiplication of three matrices such that the middle one is a diagonal matrix. But this is exactly the formula for a change of basis of a linear transformation. So, in other words, to diagonalize a matrix is to find such a basis that the linear transformation written in it is described by the diagonal matrix. Such basis and the diagonal matrix are constructed using eigenvalues and eigenvectors. So, omitting theoretical explanations, the first thing to do is to find the eigenvalues solving the following equation. The formula for the determinant of T minus lambda times I, where I is the identity matrix of the same size as T, is also called the characteristic polynomial of a matrix. Let's write down the determinant in the form of a table, do the calculations, simplify the result, and factorize the obtained formula. Hence, the eigenvalues of the matrix T are minus 2, 1, and 2. To find the eigenvectors V corresponding to the found eigenvalues lambda, we will use the formal definition of them. Let's go through the calculations for eigenvalue minus 2. We write down the equation in the matrix form with all known variables substituted, converted into the system of equations, and transform all the variables into the left-hand side. We can notice now that the second and the third equations are the same, so we can cross out one of them. Adding the other two equations together, we can quickly deduce that y is equal to 0, and substituting this information into the first equation, we get x equals minus z. So the vector xyz we are looking for has the form minus z0z, or z times minus 1, 0, 1. The eigenvector is any vector of this form, so we can choose v1 as nice as we want. Following the same algorithm, we calculate the eigenvectors associated with the other eigenvalues. The diagonal matrix consists of eigenvalues on its diagonal, and the change of basis matrix P consists of the eigenvectors, which form the so-called eigenbases. The order of the eigenvalues in matrix D must be the same as the order of eigenvectors in the matrix P. Next, we calculate the inverse of P, but we will skip the details. The matrix is diagonalized. So let's analyze what can go wrong in diagonalizing a matrix using some examples. The first one will be only kind of wrong. Consider the matrix T. Following the same steps as before, we calculate and factorize the determinant of T minus lambda times I and write down the values of its zeros. In this case, we got only one real zero, which is 1, and two complex zeros, I and minus I. The matrix T still can be diagonalized, but as T is a real matrix, the complex eigenvalues will produce complex eigenvectors, so the diagonalization will be done over complex matrices. Considering only real matrices, this matrix T is non-diagonalizable. Let's look at another example in which things are going completely wrong. Starting with the usual, simplifying and factorizing the determinant, this time we get two eigenvalues, 1 and minus 2, but the first one is a double root of the characteristic polynomial. Solving the appropriate system of equations, we obtained two eigenvectors. Following the algorithm, we put eigenvalues on the diagonal of the matrix D, and the perfectly logical thing to do is to put 1 twice, as it's a double eigenvalue. Next, we create matrix P using the same eigenvector twice. But as P has two identical columns, it doesn't have an inverse, so the matrix T is non-diagonalizable. So a good question here would be, is it true that a 3×3 matrix is diagonalizable only when it has three distinct eigenvalues? Well, no. It is true that a 3x3 matrix with 3 distinct eigenvalues is diagonalizable, but these are not all the cases. So what can go wrong while going wrong? Let's consider another example, which, by coincidence, has exactly the same characteristic polynomial as the previous one, and by that, the same eigenvalues. To find the eigenvectors, we write down the matrix equation, change it into the system of equations, and simplify it. Now, we can notice that all of the equations are the same, so we cross out 2 of them and derive the formula for one variable, for example x. Next, we write down the xyz vector as the linear combination with scalars y and z. The obtained vectors are the eigenvectors associated with the double eigenvalue 1, and there is also an eigenvector for the second eigenvalue. Next, we construct the matrix D with the double eigenvalue appearing twice on the diagonal, put the eigenvectors into the matrix P in the specified order, and calculate the inverse of P. So if there is double eigenvalue, it has to be associated with 2 eigenvectors for the matrix to be diagonalizable. Next question, can there be a triple eigenvalue for a 3x3 matrix? Of course, but this case becomes trivial very quickly. Let's take a glimpse. Assume a matrix T has a triple eigenvalue lambda 1 and is diagonalizable. Hence, the matrix D equals to lambda 1 times the identity matrix. Hence, as T is diagonalizable and the matrix D equals to lambda 1 times identity matrix, and after putting the scalar aside, the multiplication of matrices results in the identity matrix, and the total result is the diagonal matrix D. So, if a matrix has a triple eigenvalue and is diagonalizable, it has to be a diagonal matrix. So, knowing all of this, let's deduce the general rule for matrix diagonalization, but let's do it backwards. Let's have a n by n matrix T and limit ourselves only to real matrices. To do so, we have to state the matrix D, which should be filled with eigenvalues. Hence, the matrix T has to have eigenvalues with multiplicities summing up to n. Next thing is to build the matrix P, which contains the eigenvectors as columns in the order corresponding to the eigenvalues placed in the matrix D. As P has to be invertible, no 2 columns can be exactly the same, or, to be precise, linearly dependent, hence there has to be n different, linearly independent eigenvectors. Mentioning that no 2 different eigenvalues can be associated with the same eigenvector, and that there cannot be more than n linearly independent eigenvectors of any n by n matrix, we can deduce that the multiplicity of each eigenvalue has to be equal to the number of eigenvectors it is associated with. These are really nice proofs to write down. In other words, in general, over real matrices, a n by n matrix is non-diagonalizable if the sum of the multiplicities of its eigenvalues is less than n, or if the sum of the multiplicities of its eigenvalues equals n, and there are eigenvalues associated with less eigenvectors than the value of their multiplicity. So this is it. Thank you for going through this analyze with me, and if you have any questions or spotted something that doesn't look right, let me know. Bye!